Hello, my name is LUKA and I'm an architectural student at the Faculty of Technical Sciences in Novi.
And I'm Vladislav Živanović. I'm a mechanical engineer from also Technical Sciences from Novi.
So today we're going to talk about our paper regarding the integrated building design. The design is in a framework of a municipal government building located in Beijing. The authors of the paper are as follows: LUKA, Franceško, myself as the building architect, Vladislav Živanović, Berec, GABOR, and Dragan BOTIĆ as mechanical engineers. So let's see what this is about. One of the most important issues of our century is to preserve the environment. While great efforts have been made in clean energy, it is necessary for us to monitor and minimize our energy consumption. In addition to this, minimizing energy consumption will lower our cost of the building upkeep. We realized these benefits and started our integrated building design. We tested and applied multiple systems depending on their benefits and drawbacks, their potentials and their limitations, keeping in mind the logical and most efficient combination of them. After getting the results, we realized the system greatly improved the building performance and was able to minimize energy consumption and contribute to the preservation of the environment. The project goals were as follows: to create a sustainable and highly efficient municipal government building with a low energy and environmental impact. There was a tendency to approach net zero energy and reducing the CO2 emission levels. Also, to keep in mind the high level of comfort that a modern day building needs. And now Vladislav will tell you about the techniques we use to accomplish these goals.
And the techniques we use to accomplish these goals we need a high performance envelope design. We search for energy efficient HVAC design system. We determined our control lighting and luminance level controls. We used photovoltaic panels and we used PCM or phase changing materials in our floors. And for compliance we used all the energy efficiency standards, ASHRAE standards and LEED certification system.
First we're going to talk about the architectural aspect of the building. Its location, features, spaces and general atmosphere that we wanted to accomplish, making it a comfortable and well-rounded structure. Regarding location, the capital city of People's Republic of China was the location for our building. This is a beautiful, complex environment, full of interesting aspects regarding tradition and modern-day city life. This complexity fueled the inspiration for our project and for the building design itself. Next off, we're going to talk about site and accessibility of the building. When designing a building, it is crucial to analyze the building site and its surroundings. This allows you to create a structure that is in compliance with the spirit of the location, something that we call, in architectural terms, a genius loci. The site is located in the northern part of the city, called the MUNİCIPAL Road District. It's mainly residential, but along its main roads and avenues houses a big number of commercial buildings and sites. On one of these roads, called JAVNE Road, we placed our buildings, so it is accessible by car, bus, underground, and by bicycle, which is as you know, very eco-friendly. Next off, we're going to talk about the concept and the design of the building. So the idea was to design an inviting structure housing an important attribute, a municipal government building. The building design was guided by the location itself, while keeping in mind the usage of space that it provides. Its main long axis runs from the north to the south, and short axis from the east to the west. This is the same orientation as the Beijing street grid. This is also used to define the areas of the facade to be or not to be transparent. As you can see in the picture, the whole southern and parts of the eastern facade are tilted towards the ground, forming a 71-degree angle to the horizontal plane. This was done to minimize the entrance of sun's rays during the summer months, but also allowing the rays to enter the building during the winter months, thus not overheating the space in the summer and heating it up during the winter. The architectural aspect of the building was simple. providing the municipal government building with all the required rooms and spaces, but also adding some features like the skylit atrium for the office space and a large brass facade for the common grounds, which contribute to the work environment comfort. And now we're going to talk about the mechanical systems used in the building, and I'm going to let Vladislav continue.
Further, we're going to show the results and conclusions we obtained during the simulation we conducted with our plant system with some of the softwares. First, we start with the envelope. We've chosen the steel frame walls for now, and we were focused mostly on energy efficient and highly recyclable materials for our continuous installation. We've chosen one that is 90% recycled PET bottles. With the simulation conducted with Energy Plus, we obtained 70% savings in annual sensible loads compared to the ASHRAE 90.1 baseline envelope. Then we go to the lighting. Our building has window-to-wall ratio slightly above 65%. We have triple glazed, low E-coated windows, and which implies significant potential for daylight utilization and energy savings on artificial lighting. A noticeable amount of energy is consumed by lighting generally in each building, so each % of savings is actually very precious. Instead of calculating the upper lighting power density basis given by standards, we calculated them on a luminance level basis. In combination with LED energy efficient lights, we obtained 53% lower installed lighting power. And we, of course, use the lighting control, the luminosity sensors, which dim the LED lights in the perimeter of the building, and occupancy controlling device that shut off the lights in spaces that are not occupied for longer than 10 minutes. And that kind of lighting not only contributes to the energy savings, but also to the overall indoor environment quality as well. When talking about indoor environment quality, there are also some other aspects of it, like air quality, containing air humidity, temperature difference between eye level and feet level, air speed, and so on. So we try to get them all in compliance with standards. Our rooms and ceilings are 3.5 meters high. So therefore, we've chosen the on-floor air distribution for its air distribution effectiveness of 1.0. So treated air volume is reduced to the minimum necessary occupied zone. And in that manner, we kept the luxury of high ceiling and space wideness while remaining energy efficient. Small treated volume minimizes necessary airflow and energy consumption by fans. And to justify the compliance of our air distribution system with ASHRAE 55 thermal comfort standard, we've done the CFD analysis. Zandbuilder software was used to simulate air movement and temperature in two representative rooms, atrium and small office. Mean design temperature of 23 degrees during cooling season is achieved with inlet air temperature of 19 degrees Celsius. CFD analysis confirmed that the temperature difference between floor level and 1.8 meter level never exceeds 3.5 Celsius, which is mandatory. CFD, there's a difference between a small office and atrium though. In small offices, which one you see on the screen, adequate comfort is attained even with an airflow rate 50% lower than prescribed by ASHRAE 62.1. While in the atrium, there is a need for a slight increase of 6% for maintaining necessary thermal comfort. Now to get back on track. For HVAC system, we've chosen the dedicated outdoor air system, which constantly supplies occupants with fresh air, and it has heat recovery wheels for recovering heat. Minimal but sufficient airflow rate offers decrease in initial and operational costs of fans. Inlet air covers sensible and latent heat loads, whilst the airflow active shield beams cover additional solar heat gains. Sensible heat from the return air is recovered with a heat recovery wheel. Furthermore, Beijing suffers from a quite high air pollution level. To keep the interior away from direct contact with outside air, fixed fenestration is used in the whole building. Additionally, two-stage air filter system is selected for purifying air up to the required quality. Outdoor air monitoring station shifts the air between MERV 16F class filters and MERV 13 filters depending on the pollution level, so the air pressure drop is lower when the pollution level is lower. And as a result of that, less energy is spent on ventilator operation. Air handling unit heat exchangers are supplied by ground source heat pumps. The ground source heat pump system consists of 4 identical heat pumps, and each of them has heating and cooling capacity of 40 kilowatts. The example of Beijing Olympic Forest Park was used as reference for determining ground source heat pump system properties such as number of holes, depth, and diameter. They're placed on the northern side of the building. But proportional to the example, 42 holes, 150 millimeters in diameter are drilled 100 meters deep as in the example. The ground source heat pump systems and HVAC system are situated both in the basement, and all the pumps are steered by a CPU cascade control system, so only one heat pump works at low demand and all of them work at peak demand. A little bit more about the arguments in favor of selecting ground source heat pump system. First of all, Beijing has a great potential of groundwater source heat pump. It's suitable for both ground and groundwater source heat pump systems. Several ground source heat pump systems with total nominal power of approximately 150 kilowatt would cover both heating and cooling peak loads and serve as spare service water heater. Conditions in most thermal zones are similar. This means all zones can be treated by the same HVAC system, and if combined with PV panels, the CO2 emissions would be noticeably reduced. In our photovoltaic system, well, Beijing sky is cloudier during summer months than it is during winter months. As a result of that, the electricity production by PV panels is equalized throughout the year, making better balance in electricity power demand from network. Calculation conducted in Scalian's catch-up extension gave us the optimal orientation of PV panels. We have 153 PV panels, 230 watts each, with total nominal power of 35.2 kilowatts, all installed on the rooftop. Shading losses are minimal, and estimated annual electricity production is nearly 51 megawatt hour, which represents over 23% of annual electricity consumption. And PCM materials. Well, bigger window wall ratio means higher solar heat gains. Despite its triple glazed windows with low E coatings, the biggest part of cooling loads origins from solar transmitted energy through windows. PCM panels are installed in floor surfaces which receive most of the direct sunlight. They activate a temperature range of 22 to 24 degrees Celsius with approximate heat absorption capacity of 155 kJ per panel. Energy Plus simulation was done for 21st July, the hottest day in the year for case without PCM floors, as represented on the picture, and the temperatures of the floors are previewed. The table shows solar beam radiation energy transmitted through windows compared with the total heat capacity of PCM floor panels. In 3 or 4 rows stretching to 1.8 meters or 2.5 meters inside the space area. And depending on the area covered by PCM panels, heat capacity of the floor ranges from 15 to 49% of the direct solar radiation. And this feature could offset cooling peaks during summer, but also maintain setback temperature during winter nights. Besides above mentioned, constant floor temperature contributes to the uniform temperature interior surfaces and reduces interior heat exchange through radiation, thereby increasing human comfort.
Okay, so this is just the interior design using the PCM panels. So in conclusion, integrated design that we have done contribute to the creation of modern-day, energy-efficient and LEED certified administrative building with an annual electricity energy consumption of 83.5 kilowatt hours per meter square, a 17% decrease of thermal loads achieved with high-performance building envelope, 23% electricity needs covered by PV panels mounted on the roof, lighting power needs reduced by 53% through light selected based on illumination level, and an acceptable thermal comfort and air quality using adequate air filters and underfloor air distribution. As you can see, these systems greatly reduce our energy consumption, lower CO2 emission, and reduces the environmental impact. Thank you.